And I want to thank the organizers for organizing, and I want to thank those responsible for inviting me and other speakers. I want to thank them as well. I probably won't get to the Couette-Taylor burst, so we can talk about that over lunch if you'd like. What I want to do is start with the motivation. This goes way back. This is Jupiter. It's a Hubble Space Telescope image. And what you see are kind of stripes of different colored clouds. And if you actually measure this, as I've been doing with the Hubble Space Telescope now for over a decade, you can see if you plot as a function of the latitude, if you plot the zonal east-west wind, it zigzags back and forth with about a dozen jet streams in the east direction and a dozen in the west direction with some separation. They're much more widely spaced in latitude towards the equator than they are on the pole. One wants to understand the spacing and why the spacing changes and why the order of magnitude of these velocities is around 100 meters per second. That's a two-dimensional slice, obviously, from a camera. In the vertical or radial direction of the planet, the center of the planet's way down here, there's a convection zone above the stable layer here. There's a stable layer, which we call the weather layer. The temperature is like the temperature in the Earth's atmosphere. There's a tropopause and a stratosphere where things are very stratified above that. The weather layer is called that because there are a bunch of clouds. And when you look at the Jupiter, like in that last image, with Hubble Space Telescope, which uses the visible lengths, you're basically measuring things at the top of the visible cloud layer. So if you see all sorts of stripes and great vortices and whatever, you're only really measuring it at this one height in the atmosphere, and then you're making some assumptions about what might be above it and below it. With the James Webb Space Telescope, we know a little bit now about what happens above that layer. And with Juno, we know a little bit more about what happens below that layer. The approximation that I'm going to talk about today is very old, and I want to use as kind of a foil. One can simulate, if one had a good enough code, and I think we do now, the weather layer as well as the convection zone. It's a bit of a challenging problem. The Brunt-Weissler frequency goes to zero to a very large number at the tropopause and stratosphere. And so often what people do, has done for the last 30 or more years, is they approximate this as a two-dimensional quasi-geostrophic layer where it's being forced by convection at the bottom with rising and falling plumes. And so you're forcing the flow. We first started looking at that, or I first started looking at that with Harry Swinney back in the late 80s. He had a rotating annulus with holes in the bottom where he could suck fluid in and out and force the flow. And he did all sorts of things, and we did all sorts of things together. I did simulations, he did experiments. He was trying to make the polygonal zonal winds that you see in the Saturn's polar region, which has a famous hexagon there. But this kind of thing continues today. Mikhail Bar is doing things like that. He's got a recent paper in Icarus where he's got a flow that is forcing at the bottom to make zonal flows. So in this very early approximation, followed on with the work that was originally done by Vallis and Moultrud, you're trying to make zonal flows or structures by defining a potential vorticity to be equal to the vertical vorticity of del squared times the stream, operating on the stream function. It's on a beta plane because the Coriolis parameter goes to 0 at the equator and has its maximum values at the poles. There's some sort of stratification that is parameterized by a deformation radius. The deformation radius for a continuously stratified atmosphere would be the Brunt-Weissler frequency times the vertical pressure scale height divided by the local Coriolis parameter. And then there might be a bottom topography if you were doing an ocean, but probably not on Jupiter. There's really no bottom topography at all. And basically, the PV equation simply says that the vector derivative of the potential vorticity would be equal to 0, but there's some sort of dissipation that you could put in. You could put in some sort of viscosity. You could put some sort of large-scale kind of Rayleigh friction in there. And then there's this forcing, which would be pumping. They represent the pumping at the bottom by the convective overshoot. You could do the small-scale forcing, large-scale forcing, medium-scale. You could do whatever you like for the forcing. Okay, so a lot of people were doing this in the 1990s. Let's see. So this is an ageostrophic part representing the convection zone. If you were doing a laboratory flow like Harry did, or if you're doing a laboratory flow today and you didn't have a compressible or salt stratified fluid or a free surface, you'd have an infinite deformation radius, so you wouldn't have the physics of these terms. Psi would just be the stream function, there'd be no bottom topography. Both of these flows with an infinite deformation radius and a finite deformation radius are interesting. The more relevant one to Jupiter is a finite deformation radius, and they actually have very different physics for producing zonal flows. So here is a result. There was a kind of a review on this that we did in 2000. Here is the potential vorticity as a function of y or latitude, and it tends to, if we just had no flow at all, but just the beta plane, then the potential vorticity would just be beta y, and this would be a straight line over here. But the influence of the flow doing its thing tends to want to make this into a staircase where there are kind of risers and steps going out. And so one would like to understand for these kinds of forced experiments with a finite deformation radius, in some cases, you get a few zones with a certain magnitude, and I've plotted the zonal velocities here at different longitudes to give you an idea how much scatter. It's not a laminar flow, it's a very turbulent flow. Here, another type of forcing or something else is changing, and you're getting different magnitudes of velocities and spacing. So the kinds of questions we wanted to ask in those days were, let's see, are the PV cases always monotonic? It doesn't appear to be that Jupiter, if you've had PV, you could define it, is monotonic. What sets the magnitude of the zonal velocities, that is the magnitudes of the east and westward going winds? What is the length scale that is between adjacent, say, eastward going jets? What is the step size, if you will? We know that there's a Rhines relationship in geophysical fluid dynamics where the velocity is equal to the beta times the length squared of the system. What is that, with any relationship at all here? And how the beta, and I've got here E up, so we're injecting energy into the bottom, right, with this forcing at the bottom representing the top of the convective zone. Some of that energy goes to a forward cascade and is dissipated. Some goes upscale to drive larger flows. And this is the guy, the amount of energy going to larger flows is a very important parameter here, not the total amount of energy going into the system. The stuff that goes to small scales is just dissipating, it's not really important. How does the deformation radius affect all of this stuff? So these were the kinds of things that we wanted to look at back some 25 years ago. I just want to sort of set this because I want to give some idea of how we're going to improve upon this. So here's kind of a poor person's review of turbulence. So let's let a velocity of an eddy be the velocity made up of Fourier modes where you don't have the streamwise wave number of that is not equal to 0. Fourier modes where the streamwise wave number is 0, I'm going to call them part of the zonal east-west flow, right? Because there's no dependence in the x direction there. So kind of using standard turbulence, right? The amount of kinetic energy, right, here's some eddy with some velocity k, the amount of energy associated with eddies of some wave number k, I'll call E eddy of k, and kind of following kind of, 7-year-old ideas, this is an integral between k over 2 and k of the differential energy, kinetic energy spectrum, E eddy of the flow integrated over k. So if I weren't worrying about zonal flows, I just wouldn't have the word eddy here, and I would include all wave numbers. The idea of Kolmogorov 41, no matter how you slice it and want to dress it up, it's really a kind of a scaling argument that says that the rate of kinetic energy going to either larger scales or smaller scales is independent of k over some wave number, and therefore the rate that you're transporting that energy is V eddy cubed over times k. And the idea, if that's independent of k, and for this differential energy spectrum to make sense, then you've got to have a k to the minus 5/3 power. And to make everything dimensionally correct, the coefficient in front of that should be the rate of energy going into the system, or in our case, just the energy going from small scales reinforcing to large scales times the dimensionless number of order unity. So, you can dress up Kolmogorov any way you want, but it's just basically a little scaling analysis and dimensional analysis put together. On the other hand, there's a zonal velocity as well. It's a function of k. Remember, it's the one that doesn't have any all the wave numbers in the streamwise direction are 0, so it's made up of those Fourier modes. The amount of energy at some wave number k, I can define as E zonal of k. Again, it's an integral, a logarithmic integral between k over 2 and 2 of whatever the differential spectrum would be for the zonal thing. And from, understanding that from dimensional analysis and scaling, we expect the zonal velocities to be proportional to beta. This is basically the Rhines relationship here, which says that the length scale, the velocity is equal to beta times a length squared. That and some dimensional analysis tells you that the eddy differential spectrum, you expect to be of order, some dimensionless number of order unity times beta squared times the k to the -5, not a -5/3. So the total kinetic energy spectrum is made up of the zonal piece plus the eddy piece, and they have different relations, dependence upon the k. There must be some values of k, some value of k where these guys are equal, right? This zonal piece is going to dominate like crazy for large scales or small k's. The eddy piece is going to dominate for large k or small scales, but right, there's some, if I set this term equal to this term, and define that with a value of k where they're the same, as I call that k sub r, it tells me the separation, right? So for values of wave number less than kr, you're going to be zonally dominated, otherwise you'll be dominated by the vortices. And sure enough, if I plot the kinetic energy for one of these turbulent flows as a function of wave number, and the solid lines are the zonal piece, the dashed lines are the non-zonal or eddy piece, and it's fluctuating in time, so you see a lot of different graphs here. But basically, even though the thing is highly time-dependent and turbulent, this guy looks like a k to the -5, and this part over here looks like a k to the -5/3, and this arrow represents, I'm doing very narrow band forcing in this set of experiments, and so we kind of get, right, what we thought we get. We've got a composite spectrum of a zonal part and an eddy part, and they cross at some wave number k sub r. And sure enough, if you look at this guy, you can calculate, here's your injecting, basically energy's a forward dissipation of energy and things go away. Back here, you're doing an inverse or backward cascade of energy, and you're creating these two spectra that cross. And sure enough, if you look at the flow, this looks like a bunch of vortices, and at these scales, it looks like a zonal flow. The largest energy, if you somehow make it to here in your inverse cascade, it's going to be the zonal component of the spectrum that dominates it, and you see mostly zonal flows. If for some reason things poop out and these spectra only, say go up to here, and you look at it qualitatively, you say, oh, it's a bunch of turbulent vortices, I don't see zonal flows at all. And that pretty much summarizes what our experiments were. But the question is, what does decide the wave number where these spectra, basically from thinking of a reverse cascade, where do these guys stop? Okay, and what seems to work really well for our numerical simulations, and which seems to work well for Jupiter, is the following. The total energy of these stratified flows, and this is why experiments with a non-free surface of constant fluid or different, right? If you're stratified, you've got both the kinetic energy and potential energy. And these guys are functions of wave number. In fact, in this quasi-dystrophic world, where the velocity field is just the gradient of the stream function crossed into the orthogonal unit vector, right? The kinetic energy at some wave number k is just the stream function at that wave number, absolute value squared divided by 2. But the potential energy is just the stream function squared divided by the deformation radius squared. So there's a very, very clean separation between kinetic energy and potential energy for any given wave number. And again, one wants to know what is the ratio as a function of wave number of the kinetic energy to the potential energy. So just dividing these guys, the size go away, and it's just k squared times LR squared, which means for small wave numbers or large lengths, right, your potential energy is going to dominate your kinetic energy. All right, so when are these guys equal to each other? They're equal when the kinetic energy is equal to potential energy, or equivalently, this k bar is basically the deformation radius itself. So the length scale then associated with this crossover, where the kinetic energy suddenly loses dominance, the potential energy is going to be 2 pi times the deformation radius. Well, right, going all the way back to Kolmogorov in 1941, the concept of eddies going around in energy cascades say that kinetic energy is the quantity that cascades. You look things up and no one ever talks about potential energy cascading, so that's really important. If I'm starting at really small scales and everything is kinetic energy dominated, I'm just going to inverse cascade, and then I get to the point where it's all potential energy, and that's where the cascade stops. And so, schematically, that's going to look like this, here's where we're forcing. Here is the zonal part of the energy spectrum. Here is the k to the minus 5/3 vortex part of the energy spectrum. Once you get beyond this kr, right, we're going to be mostly dominated by the zonal part of the velocity. And where will this stop? This is going to stop at a wavelength such that that wavelength is going to be 2 pi over the largest scale I'm going to make, which is 1 over LR. 1 over LR is when everything turned into potential energy. So if everything becomes potential energy at this point, you wouldn't expect any more inverse cascade. Right? You've kind of done your thing. And that agrees really, really well with not only the energy spectrum we calculate, but more importantly, when I go back to the zonal flows that this guy created, if I plot my potential vorticity as a function of latitude, it made this kind of step-like function. The steps over here, the width of those steps is going to be my largest length scale, and it agrees very well with that very simple analysis. So I think in the case of a simple quasi-geostrophic flow with finite deformation radius, when you force in a narrow band at small length scales, this is what determines the size of the steps. It's the W, and since the straight line that it's perturbing is just determined by beta y, that will then tell you the size not only of the height but of the step size itself. You can invert the potential vorticity to get the zonal velocity. If this were exactly step-like over here so that the steps had constant potential vorticity, then when you inverted that with finite deformation radius, you get a bunch of cinches linked together to create a zonal flow, and it would look something like this. It would look like, here is one cinch, which represents one part of the step where the potential vorticity is homogenized. Below that, there's the next cinch, hyperbolic sign. So that's kind of what's going on. And I think that is a pretty good description of what we found some 25 years ago. And so this is making, right, staircasing. It's making layering, not of salt, not of density, but it's making layering of potential vorticity. And that's the key point here. It's potential vorticity dynamics that's getting layering. Often, unless you're very, very lucky, what we find is the flow, which is very turbulent, it's kind of meanders a bit. Right? This flow happens to have 10 eastward going jet streams, but every now and then it doesn't like that. Ooh, I want to make 11. So it suddenly makes 11, and there's a burst of energy then. And then suddenly, now and then it decides intermittently to go back to 10. And so it goes back and forth between n and n plus 1 zonal flows, or n plus 1 steps in my staircase, and that leads to really big turbulent bursts. And I'll show you an example of that in a movie in about 15 minutes. Was there a question? Yeah.
When you say it agrees, do you mean it agrees like an order of magnitude, or like can you distinguish between 1 over LR versus 0.8?
I'm glad you asked that question. I'm very glad you asked that question, because the answer is yes, if you kind of keep your eyes closed. Okay. So, so basically, this would say that let me see if I've got this here. Now let's do. Okay, so all right. So my claim is that 2 pi times the deformation radius should be the distance between adjacent eastward jets on Jupiter. And that quantity is the vertical pressure scale height. So when I look at the clouds from, say, the Hubble Space Telescope, at that level, regardless of latitude, H is pretty much the same of about 32 kilometers. The Brunt-Weissler frequency divided by F, right, on the other hand, changes. The Brunt-Weissler frequency depends upon the stratification, the temperature as a function of pressure, or temperature or pressure as a function of height in the atmosphere. And that's pretty close to being a constant number. That's been measured now by Juno, the James Webb Space Telescope, and Hubble, as well as infrared measurements from the ground. So N is pretty much independent, as is H, but F is the Coriolis parameter, which is 2 times the angular velocity at the North Pole, right, times the sine of the co-latitude, right, where 0 of the latitude is at the equator. So it's going over 1 over F, so therefore the LR is very, very big towards the equator and decreases as you go towards the pole. So if I plot H from observations divided by N from observations divided by F, because we know the rotation period and the pole. If I plot this quantity, multiply it by 2 pi, and put it on that graph at the top that was measured originally by the Voyager spacecraft in 1979, it's a quite good fit. All right? But on the other hand, it's also a bit of a lie. And why is it a bit of a lie? It's a bit of a lie because all of this might be a bit of a lie. Jupiter is much more complicated than a fluid with a constant Rossby deformation, a constant Brunt-Weissler frequency as a function of height. At the top of the convective zone, N over F is 0. At the top of the red spot, right, N over F is probably on the order of 300. It's highly variable, and if you believe the thermal wind equation, which is a relationship between quasi-geostrophic balance and hydrostatic balance in the vertical direction, it tells you that there's a relationship between the vertical derivative of a horizontal velocity and a horizontal gradient of a temperature. So we've got temperatures above the cloud level where the Hubble Space Telescope measures things. And if you use those temperatures, take their horizontal gradients, and look at one particular latitude of what the zonal flow is, right? So this is what I showed you back on the second slide, the velocity, which might be about 75 meters per second, going in that direction as a function of height. If the thermal wind equation is really appropriate, it actually decreases flip sign and then goes zooming back to a much larger thing as a function of height. So this pressure in bar is a logarithmic pressure of the mean pressure of the atmosphere. So typically, instead of height on Jupiter, you talk about what is the mean pressure. So this is high, where the pressure is 10 to the minus 3. This is deep in the atmosphere, where the pressure is of order unity. So, if I want to say, oh yeah, I've got this great code, I've got this great laboratory experiment, and look, I can reproduce Jupiter's zonal velocities, I would go, really? At this height, or this height, or this height, or this height? So you've got to bear that in mind, that there's a lot of slop in this system, right? Producing zonal flows is not necessarily Jupiter. Moreover, all the dynamics that I talked about was based on potential vorticity. Right? If I did 2D QG, you could do 3D QG, but the Ortel's potential vorticity, which is the absolute vorticity, dotted into the gradient of some scalar lambda, such that the effective derivative of lambda is equal to 0 divided by density, right? That is the heart of all these equations or stability theorems, numerical calculations. It's all based on the idea that maybe there's a potential vorticity. In order to use the potential vorticity of an atmosphere, you generally want to have lambda, the entropy, because the effective derivative of the entropy is approximately 0. It's not a very dissipative system. And therefore, you're going to get the vertical component of the relative vorticity plus the absolute vorticity of the rotating planet, 2 times its angular velocity. And the problem is with this guy is that, let's see, is is that, right, I can define potential vorticity very well here. Potential vorticity has no meaning whatsoever inside the convective zone if you're using S, the entropy, because the gradient of the entropy is approximately 0. In fact, well above the top of the convective zone, the gradient of the potential vorticity in the vertical direction is actually dwarfed by the component of the gradient of the potential vorticity in the direction from the equator to the pole. So when you take that vector, right, and dot it into the absolute vorticity, you're not dealing with the quantity you thought they were dealing with. So the whole question, there's a big worry about anything that's based on potential vorticity dynamics may be kind of a fraud if you want to apply it to Jupiter. And there are a lot of people out there, many on this university, starting with Michael McIntyre, who's very concerned that you cannot separate a quasi-geostrophic weather layer and do dynamics on it where you're forcing it at the bottom from a convective zone. That's kind of a cheat. You're taking your fluid dynamics and arbitrarily dividing it into two regimes where one is you've got the equations for it and the other ones you don't. And so you really should probably treat this as a system unto itself, one unified system. And so we're actually preparing to do that. It's a numerical challenge, but I think we're ready for that challenge because we've certainly done this with not the zonal flow, but with the Great Red Spot of Jupiter. And my student, Adi Zhang, had a nice poster on that in the room yesterday while everybody was drinking wine. Okay, so I want to give you a similar problem that's a little bit more recent, that's very, very similar. It's going to have zonal flows. It's going to avoid using potential vorticity, and we're going to see what it does. And so this is a late-stage protoplanetary disk. So when stars form, you get a collapsing cloud, and in the late stages of collapse, you've got a protostar that almost has the mass, but not quite, of the star that it's going to form. And around that star is a cold molecular hydrogen disk of gas. And this disk of gas has some dust grains in it. And so people are very, very interested, right, at the Institute of Astronomy, they're very interested in these accretion disks of how does that dust get together and form the core of planets? How does angular momentum get out of that disk so that things can fall into that protostar and make a full-size star? These are ongoing questions. But right now, since this is a math institute, not an astronomy institute, I'm just going to say that right in this stage, the hydrogen gas going around the star is in an approximately Keplerian orbit because the amount of mass in the disk is not very significant to the amount of mass in the central star. So we can use freshman or high school physics and say, that gas is roughly in Keplerian orbits. The gas is really, really cold. It is, how cold is it? It's so cold that you can't get ionization basically out of it. And there are a lot of interesting magnetohydrodynamic instabilities, such as MRI, that control the disks around high energy objects like neutrinos, like neutron stars, but this guy over here is really cold, so you can just forget. There may be magnetic fields, but since they can't couple to any ions, because there aren't any ions, we can ignore magnetic fields. So it's purely hydrodynamics of this disk that I'm interested in. And the viscosity is small in the sense that the Reynolds numbers are huge. We're talking about astrophysical lengths, astrophysical velocities. If you take the viscosity of molecular hydrogen, you're going to get Reynolds numbers of like 10 to the 20th. So we're not going to worry about dissipation through viscosity. On the other hand, and this is debatable, and I'd like to talk to some people here because there's a controversy, there is a cooling time, right? This gas does have some heat associated with it, and it's going to want to cool. But it is so cool, it's not very effective at cooling by itself. It has to interact with these little grains out there, and those grains are kind of like gray bodies, and they radiate. But there's a lot of interesting complex physics between the gas and the grains that will tell you what the cooling time is. So we've done a lot of those calculations, and we have found that those cooling times are significantly longer than the rotation period of the disk at the radii of interest. So I'll be happy to talk about that controversy over lunch with anybody. But the disk this disk is characterized by 3 numbers, and all of them are, have dimensions of 1 over time. There's the Coriolis parameter of this disk going around the star, right? So it's 2 times omega of the disk, and omega is a function of radius because it's a Keplerian orbit. There is the shear associated with that Keplerian orbit. It's a very important piece of physics in this problem. And the relationship between the shear and the Coriolis parameter for a Keplerian velocity, since I know what a Keplerian velocity is and I know how to differentiate, it's just, these guys are related to this guy by a factor of -4/3, so they're roughly of the same order. And there's the vertical stratification of the disk. This is the plane of the disk. There's stratification above it and below it. By symmetry, the temperature here is the same as the temperature here, so there's no gradient of the temperature at the disk due to the symmetry. So it's completely unstratified at the midplane of the disk, and the stratification parameterized by the Brunt-Weissler frequency increases like crazy as you go above it and below it. That's the main physics that I want to talk about. Rather than simulating the entire disk, I just want to look at a little portion of that disk and explore the shearing, rotating, stably stratified flow there. That's a very standard approximation called a shearing sheet approximation. The advantage is it allows you to put some boundary conditions in the radial direction. Okay, but the idea is basically it's plain Couette flow at the lowest level. So plain Couette flow, right? You've got a linear shear. This is my streamwise direction x, though astronomers call it y. We won't go there. So there's this linear shear here, sigma, and we want to explore the physics of that. The cross-stream direction I'm going to call y. When I think of this as a little patch of fluid in a disk, this y cross-stream direction becomes my radial direction because I want to go into the rotating frame of some piece of Keplerian moving fluid here. And if I do that, I will see the velocity going one way this way and going the other way at a different radius, and so I get, to first order, a linear shear there. So my azimuthal direction, now my streamwise direction, and for Keplerian shear, the vorticity of the shear has the opposite sign of the omega going around the planet, so it's an anticyclonic shear. If this is stratified, it would be stratified in this direction coming in and out of the board. If I had the disk midplane, n would be equal to 0, but n would increase as I go upward or downward into the wall here, depending upon what I'm using to either model, because I really can't observe, the temperatures as I go away from the disk. With just good old plain Couette flow, you can calculate it's neutrally stable to linear eigenmodes, right? All the linear eigenmodes are neutrally stable, an unbounded Couette flow system. Even if I had rotation around this axis over here, there's my Coriolis parameter equal to 2 times the rotation. It's also linearly neutrally stable. And when I stratify it in the vertical direction coming in and out of the board and define my Brunt-Weissler frequency in the usual way, this, if I were dealing with salt stratified water, would be the density. If I were dealing with a gas, this would not be the density, it would be the potential density. But this guy also over here is, you're going to find that, at least for constant Brunt-Weissler frequency, that it's also neutrally stable. However, there's some really interesting physics here. This flow has critical layers. So in a traditional critical layer comes about in a unidirectional flow, right? So the cross-stream direction is y, the streamwise direction is x. So I've got some flow that, some equilibrium flow, V bar, dissipationless. It turns out if you calculate the linear eigenmodes, and there's an eigenmode that's traveling in the streamwise direction at any location y star such that the V bar of y star, the velocity of the unperturbed flow at that latitude, or that radius, is equal to the phase speed of the instability. That forms a critical layer. Okay, so Kelvin was the first one, I believe, that talked about critical layers. He talked about cat's eyes. Mathematically, if you write down the governing equation, which for just a constant density fluid would be Rayleigh's equation, if you write down an equation for the stream function, the highest order derivative term, if the coefficient of that ever vanishes, basically you have a possibility of a singular solution. And so the coefficient in front of the highest derivative term, when that's equal to 0, which for that value of y, or y star, where that is equal to 0, that's where you get a critical layer. So the point is that when you stratify in the vertical direction, you get a new set of critical layers that no one had ever seen before. Me and my graduate students, I had looked at this problem. Just normal critical layers are really hard to excite. You can whack them in the lab, maybe you'll get a Kelvin's. Not much happens. These guys, you look at these guys cross-eyed and they explode on you. They're very, very unstable, these new critical layers. Well, that's why they're important. We discovered them accidentally while we were doing numerics. First they thought, oh, it's a numerical problem, an error, but then we actually analytically went and worked through them and found that our numerics were doing the analytics right. So basically the location in the middle, a critical layer, is y star. So the coefficient from the highest derivative of my governing stream function equation in the usual case is just equal to the velocity of the flow, which is a function of y, the unperturbed velocity, minus that should be a subscript there, minus the speed, phase speed of the wave. So if I'm looking at normal modes where I've got a wave number in the streamwise direction kx, I've got a phase speed cs, the frequency associated with that is related to the phase speed in the wave number in the usual way. So where this guy is equal to 0, right, at those locations where y star is such that this term is equal to that term, that's where I'm going to get a critical layer. But if you add vertical stratification, and I'm doing this for just a Boussinesque fluid because it's easy to explain, and in fact it's a homework or problem I regularly assign my students, my first year graduate students, you get that the coefficient in front of the highest order derivative term for what has now replaced the Rayleigh equation has a second term in it, and if this term is equal to 0, you get a new kind of critical layer. So this is the old, boring, old-fashioned, very stable critical layer. It's a barotropic critical layer. It doesn't have any Brunt-Weissler frequency in it. This is the new baroclinic layer, and critical layer. It's got the Brunt-Weissler frequency in it. It's got basically the frequency of the wave in it, and it's got the wave number in it. When that is equal to 0, something interesting can happen. And so when y star is when this term in brackets is equal to 0, and if I just do a linear Couette type problem as a simple example, where v bar y, the unperturbed equilibrium, is known as just Couette flow with a constant shear, then I can solve for the location of the critical layer. The critical layer that always dominates in our calculations, or our numerical calculations, is the stationary one, where the frequency is equal to 0. That's the one that dominates. The physical explanation for that is as I've got differentially rotating flow around a disk, or if I've made it Cartesian and periodic boundary conditions on it, if I have a disturbance here and a disturbance here, right, basically the time that these two disturbances come back together again, if that time is 1 over the Brunt-Weissler frequency, that is the location with s equals 0. It's that resonance of the oscillation in the vertical direction, that period being the same as the period where the differential rotation brings two objects back together again, moving along with the unperturbed velocity field.
Bill, are you assuming that n is constant?
Yeah, so for this I'm choosing n is constant just so I can do an analytic calculation for it. But numerically it's easy to do it with non-constant n as it is with. And I'll show you those numerical simulations in a moment. So what this says is that y star is n over sigma kx, but this is a periodic system, there's no origin. And it's self-similar. What this really means is that you're not going to get one y where there's a critical layer. You're going to get an infinite number of y's, and those latitudes, or radii of my disk. And the spacing between critical layers is going to be the Brunt-Weissler frequency divided by the local shear, which again I'm assuming constant here, times the wave number in the x direction of the perturbation that I'm looking at. So these critical layers are fantastic. They can explode with lots of energy. Where do they get their energy from? The same place that Couette-Taylor flows get their energy from. You take a Couette-Taylor system between two differentially rotating inner and outer walls, you've got the velocity as a function of radius. The flow, when it becomes turbulent, wants to make the angular momentum at each radius the same. It wants to make that uniform. When you go from that differentially rotating thing to the special differentially rotating thing with constant angular momentum as a function of radius, that's a much lower state. And that difference between those two energy levels is what drives the system. Here, what's driving the system is this huge amount of energy associated with the Keplerian flow. If I were to make that constant angular momentum that made it differentially rotate that way, then I'd go to a much, much lower energy state. It's that difference between those two energies that drives all of the instabilities that one sees in critical layers. So there's basically a vast infinite reservoir. So let me show you a movie. I'll first show you the movie for constant shear and for Boussinesque and for constant Weisler frequency, and then I'll go into a more realistic representation of that. So here is the plane Couette flow, where this was my streamwise direction, or equivalently, this is the direction, the azimuthal direction around my protostar, which is way down there, okay? So this is the radial direction, this is the streamwise direction. Let me turn that on its side 90 degrees, because that's the way the movie is. And so here is a movie. A green pixel represents the color, the vorticity, the vertical vorticity coming out of here of the unperturbed Couette flow. The color will represent, will either be a red, green, blue spectrum, where it's going to be either positive or negative. And this is actually a piece of a computational domain that is much, much bigger than this, okay? Because I didn't want to have to worry too much about effects at boundaries and things. All right, I'm going to put in a little bit of small noise here, and I'll talk about the noise in a moment. And I'm going to see what happens if I just turn the initial value equations on. Here's what I get. All right, I've chosen my units so that this is equal to the spacing between one critical layer. I get a disturbance here. The critical layer starts producing a double dipole of vorticity on either side. It excites the next critical layer over, which excites the next critical layer over, which excites the next critical layer over. Okay, we made this movie one evening, Halloween evening, and we said, let's call it the zombie vortex instability, because it just infects everybody as you go on forever and ever, until everybody looks like a zombie. In the vertical direction, this is the streamwise direction, cross stream is coming out. If I start off with a little isolated patch of vorticity, again, this is a grayscale of the vertical vorticity, after a certain amount of time, if I put viscosity in, I can actually come to a stationary state, not an equilibrium. I can make a crystal lattice of these zombie vortices, okay? So that's interesting. It's not astrophysics because it has too small a Reynolds number. So what I'm really interested is in doing this for a Brunt-Weisler frequency that would be acceptable to astronomers who are looking at a protoplanetary disk with 0 Brunt-Weisler frequency at the disk midplane and getting higher and magnitude as I go away from the disk midplane. But before that, I want to say that these instabilities, I said, they're neutrally stable linear. These are not linear instabilities. These are finite amplitude instabilities. And unlike most finite amplitude instabilities that I'm used to, it's not an amplitude of the velocity that matters. It's the amplitude of the vorticity that matters. You've got to get that over a certain critical threshold. And that's really important if one is introducing noise or turbulence as an initial condition. Let me come through this really quickly. If I've got a differential energy spectrum, what goes as k to the minus a power, so for Kolmogorov, it would be 5/3. That means that RMS velocity at any particular wave number goes as k to the 1 minus a over 2 power, or the velocity at any particular length is going to scale as that length divided by the biggest length to minus 1 minus alpha over 2. The vorticity scales in a different way. I just multiply the velocity by a k, so they scale differently. The point is, for a's between 1 and 3, like 5/3, the vorticity peaks at the smallest scale of the system, whereas the velocity peaks at the biggest scale. So normally we don't care about vorticity, but here we care about vorticity. Here we've got this big energy over here in the big length scales, and we go down here, oh, the velocity is going to 0. But the vorticity is the opposite. The smallest scales have the biggest vorticity. So if you have a very large spectrum, is what you would have in Kolmogorov experiments or in an astrophysical situation, right? There's a lot of small length scale you can get to, so the vorticity can become very high and over this critical threshold. So we did a lot of experiments on that. And so that's how I'm going to initialize the flows, which I'm going to show you in a moment. These instabilities, I say, the flow is characterized by 3 inverse timescales: the Brunt-Weissler frequency, the shear, and the rotation or Coriolis parameter. In a Keplerian disk, the shear is a slave to the Keplerian velocity or to the Keplerian Coriolis parameter. They're of order unity. We always find that these guys have to be of the same order, right? The ratios order unity. They have to be of the same order for this instability to work. Turns out that the Brunt-Weissler frequency also has to be of the same order as F and the shear for this instability to work. There's a special part of nature that has this. We can't find it anywhere else. So for Keplerian velocities, for the format of the temperature as a function of height in the disk, for those we found that this instability requires that the Brunt-Weissler frequency divided by the Coriolis parameter must be between somewhere 0.6 and 2.1. Remember that the Brunt-Weissler frequency at the midplane of the disk is 0, so this is not going to happen here. As you go up to about 2 pressure scale heights above and below the disk, you start getting in this range, okay? If you go up too high, you won't be in that range anymore. So the question is, right, this is like the Jupiter problem, right? So this is my late stage protoplanetary disk, right? We're interested in what's happening at the disk midplane because that's where all the mass is. You have to go up a couple pressure scale heights above and below the midplane before you find that the Brunt-Weissler frequency, the Keplerian shear, and the Keplerian Coriolis parameter are all the same. So it's at some special heights above and below the disk of about 2 pressure scale heights where this instability is going to happen. It's not going to happen anywhere else. So the question is, this is kind of like our convection zone in the Jupiter problem. If I drive my system here, will it really drive zonal flows all the way down to the disk midplane where I want to see them? And since the Brunt-Weissler frequency is changing as a function of height, that means the separation between critical layers is changing as a function of height. Is it going to remember this height here, or is it the separation between critical layers going to be a function of height? So we can answer those questions numerically. So no zombie growth at the midplane, grows quickly above and below by a couple pressure scale heights, and then it doesn't grow very fast at all. Okay. All right, let's see. So that's what I say. This is similar to this problem in Jupiter, where here's our forcing way down here, but we want to know what's happening up here. Okay, so, but here we're actually going to do the numerical calculation and answer that. So this is the streamwise direction of my slice of disk. This is the z, the vertical direction. So at z equals 0 is the midplane of the disk where there's no Brunt-Weissler frequency, no zombie instabilities. This is my radial or cross-stream direction over here. I'm plotting vertical vorticity, and I'm starting off with the Kolmogorov spectrum of noise, and that's why basically at the smallest scales of the numerical resolution, that's where I'm seeing my vorticity. It's at the smallest scales possible, right? So let's put in the initial value equation and turn it on, and this is what you get, all right? This is the streamwise direction, right? Somewhere above and below the disk, it's trying to make critical layers. After a few thousand years, we're seeing this, the vertical vorticity is kind of organizing itself as stripes, and it's invading the disk midplane where there's no zombie vortex instability, and it's keeping the separation between adjacent critical layers because the vertical vorticity is becoming staircased, and it's following the critical layers. So you think of critical layers as very delicate things. This is highly turbulent. So let me just show you, right? So after a short amount of time, right, you start seeing the zombie instability coming in a couple pressure scale heights. These are in units of pressure scale heights above and below the disk. Not much happening at the midplane. And then it starts filling in. And so you're seeing steps in the vertical vorticity. When I integrate that, right, I'm saying plus minus in vertical vorticity, that's going to give me steps in the Keplerian velocity. And so I'm going to cycle through, right? So here is my velocity in the azimuthal direction, This is the Keplerian velocity, the dashed line, and the numerical simulations, this is at kind of late times, it's kind of producing steps, where the difference between this point, that distance, and this distance radially is the distance between the critical layers at about 2.5 pressure scale heights above or below the disk. This is what the vertical vorticity looks like as a function of time during one of these burst cycles, and it's just like the planetary burst. What it's doing is it's changing the number of steps. It's trying to reduce one, and then it bursts when it does that. It's now, I don't like this. I'll go back to what it was. No, I don't like this. And it intermittently bursts because it's changing the number of steps in the system. So basically, that's it. The ZVI is a finite amplitude instability. It produces steps. The width of the steps is really the critical layer separation at the point where the zombie instability grows the fastest. We basically want to do the same thing using the new code that we developed that can take very efficient time stepping for the Jovian atmosphere where the Brunt-Weissler frequency changes like crazy from the top of the convective zone to the tropopause. We want to see, we do our calculations that I showed you in the first third of this talk using the full three-dimensional system, not making any geostrophic approximations, not using potential vorticity. So thank you very much for your attention. Take any questions.
Questions, please.
When you said at the end that the zombie vortex gives you a highly turbulent state, how do you quantify the highly?
Okay, so, all right, so I don't. Basically, I look at this and say, right, from 30 years, 40 years of computing things, this is not a quiescent laminar state. Okay, so I don't have for you, I could come up with a definition of what I mean by turbulent, but let me just simply say, that's not laminar, okay?
No, but I mean, the very fact that you've got such stability with your critical layers indicates to me the fluctuations in the zonal flow are small compared to your base shear.
That's correct. That is correct. So yes, these velocities compared with Keplerian velocities are small. But to me, it's amazing that critical layers tend to be such delicate things in the lab that it could survive that kind of thing. So yeah, I will phrase it maybe as not turbulent. I don't know what it is. Compared, the velocities that are fluctuating are small compared with the base state, though. And they're.
Could you quantify what small is? Could you put a number on it in terms of the ratio of energies?
Right. I mean, what I'd really like to do is if I want to quantify, I would come up with fluctuations in time and the scales, plot PDFs and all that stuff. Yeah, that would be the right thing to do.
What that number would be?
I don't know what that number is off the top of my head. Yeah.
Benjamin?
So first part, when you argue that what stops in the cascade is the fact that you go from kinetic energy to potential energy.
I have to forgive me. I can't hear very well, so you're gonna.
So in your first part, when you argue that the inverse cascade stops at the Rossby deformation radius, when you go from kinetic to potential.
Right.
I mean, the potential energy is still some kind of invariant of your system.
Right, so-
You expect cascading. Why do you said
Okay,
that
so,
cascade?
All right, so two things. First of all, when I do the numerical experiments, I pretend I don't know any theory I know. I don't want to bias myself. I just want to say, let me try and change all the parameters. I want to know where the step size is, where the cascade stops. And just doing that, you can fit all the data very lovely to, it's 2 pi times the deformation radius. So then you go and say, why is there a reason for that? And you say, well, at that wave number for that, then basically I'm suddenly dominated by potential energy, not kinetic energy. So if I assume that the inverse or reverse cascade depends upon the kinetic energy dominating, then I can explain that. So think of that as an empirical result rather than a theoretical proof that potential energy can't cascade. In this situation, we just don't see it. We tried really, really hard to do that. But once we build a numerical code, we don't want to bias ourselves and we pretend we're just in there doing experiments, moving knobs around.
So if in the case where you don't have a finite deformation, was your radius then need to invoke a completely different argument to say that the cascade is up?
Right. So when you don't have a deformation radius, you can often get stepping And I think, you know, in the experiments in Marseille, you got stepping. But what we found was it really depends upon ratios of the dissipation, the dissipation that would be due to Ekman pumping, the forcing, and things like that. Right. But it would be a different physical mechanism, obviously. Oscar?
Do you understand why the number of steps change?
No, I do not. That's a very good question. What we started to do, but became expensive, was to say, is there a sweet spot in our computational domain? If I adjust my domain just right, I can stop it from bursting and oscillating back and forth. We never did that just because of the expense became too great. But no, I would love to have a theory for that.
I'm going to be chairmaniacal and get in a follow-up question on that. In many of the reduced models for layering we play around with, you see, of course, mergers, which is a step change. But what happens is that it's a progression toward coarsening. Mm-hmm. You seem to be saying it coarsens and uncoarsens.
Uncoarsens, right.
And I mean, do you understand what's
no.
going on there?
No, originally we saw, okay, yeah, the stripes are merging together as a function of time. They're going to do their thing because they started out with really small scales. But we were surprised, and we do not have a theory for why they decided to split apart again. No. That's, you know, I could have had a last slide of things that we don't understand that will be good for future research.
All right.
Yeah, to go back to the questions you understood at the beginning when you talked about Protoplanetary disk, do you know about the angular momentum transport for this instability? Is going outward, inward?
Come on, I have, one of the things I got to get a hearing aid, can I say?
My question was related to the way you introduced Protoplanetary. It's one of the big questions for angular momentum transport. So I wanted to know if you've looked at that for the zombie vortex instability, if angular momentum is going outward or inward, and at which rate.
So you're asking about the transport?
Of angular momentum.
Of angular momentum, right, okay. So yes, that is on our list of we did some crude calculations, and we find transports of angular momentum in the kind of right direction that protoplanetary disk people using their values of alpha that they like in order to finish the completion of the star. But I would say at the moment it's a kind of a delicate thing, and we have not looked into that. Right now what we're really spending our time is looking at the cooling times, because for the cooling times, you want to start off with a polydispersed distribution of grains, right? And the grains are going to be, some are going to settle, some are going to be lofted by the, I don't know if it's turbulence, but the eddy motion there. And one wants to understand what is that distribution of grains, the density of the grains for each radius as a function of height above the disk, because that determines the whole game with respect to cooling times, because we require a cooling time that is 8, 9, 10 times at least longer than the year, the circulation time of the Keplerian velocity, whereas almost all the other purely hydrodynamic instabilities require incredibly fast cooling times. And when we ask our dear colleagues, and they are dear colleagues of us, is why did you use that fast cooling time? Oh, because it gave us the result we wanted, right? It's very difficult to calculate. I mean, there's a whole history of this with Chris McKee calculating cooling times. And so we kind of went through his version of it, but when he calculated cooling times, you know, he just assumed that there was a distribution of grains of a certain size, a certain distance from the disk. He didn't put in the dynamics of how they would they continue to settle out, would they be relofted, and you really got to do that to do the calculation right. And so we're doing that with a two-fluid model right now, monodispersed version first. But it's a really good question.
All right, we'll give the last word to Guillaume there.
Back to the uncoarsening, when you say your staircase rearranges, you get a big burst of energy. But the turbulence itself, especially in the Jupiter case, since you have the convection, it can produce bursts by itself. So what do you have seen the effect of the burst generating or nucleating?
Okay, so when we see in, let's see, so in the protoplanetary disk calculations, when we see the burst, we don't see anything happen with respect to thermal convection, because you're typically, everything's happening far enough away from n equals 0 that you're going to be really straight. You're not going to have many local convective instabilities. So what we found, when you look at the energy, right, there's got to be a balance. Basically, there's very little dissipation in the system. So the energy that goes into the burst of these very small scales is ripping off kinetic energy from the differential rotation associated with the background Keplerian velocities. I mean, energy is approximately conserved in the system. There's a net loss of kinetic energy because we have some, in those calculations I showed you, we have a hyperviscosity in it. In the calculations where we have really cranked up the cooling time to basically infinity, we have a hyperdiffusivity as well, or we could. The problem is when if you really want to do it, it's optically thin, and therefore you can't represent the cooling by conduction. So in those calculations I showed you, there's simply a hyperdiffusivity. Hyperdiffusivity works in a funny way. It can both, unlike hyperviscosity, which monotonically decreases kinetic energy, hyperdiffusivity can increase the potential energy as well as decrease it. So comparatively, we've looked at how much energy is coming from the hyperdiffusivity, and it's negligible compared with what we're ripping off from the Keplerian disk motion.
All right, I think it's coffee time. Let's thank Phil again for a wonderful talk.